Welcome everyone to Institute of Analytics Global Webinar. My name is Netra Sambamurthy. I am the promoter of Institute of Analytics, and I also teach at Institute of Analytics. And I have my colleague Jasrel Kemani, who is a researcher and also instructor at the Institute. So it gives me really a great pleasure, as well as it's exciting to meet you all. We meet every month on this topic, and today we have really an exciting topic for a reason. I'll explain that. As you all know, image recognition means neural network and deep learning, and let's just make it as learning methods, okay, rather than saying anything else. Learning methods, but more so, and actually only neural networks, nothing else. But we have found traditional methods like density-based clustering methods, that is also called DBScan method, can do the same image recognition. Okay, you get it, everybody? Density-based, how dense the points are, and how the density of points is giving rise to types of images. Okay, can also serve the same purpose, and that is our innovation, really. So we are today presenting. We will review. This is what we are going to do today. This is being recorded, so I will post it. So I wish people join early than later, but if you have just joined, don't worry about it. The way we are going to present this as follows. Last time we reviewed UNet, a network that is looking like U-shape. Are you able to hear me? Please give me some input. Are you able to hear me clearly? You should be able to hear me clearly. People who are joining should mute out their phones, okay? Are you able to hear me? Please give me some input, please. Okay, Anurag says, thank you very much, Anurag. On a clarity level, 1 is the best, 10 is the worst. Where would you put it? 1, excellent, Anurag. Thank you. If one person says 1, I think it is more of a really on your side if you are not able to hear, okay? Thank you. Cool, very cool. So let me go back and how we are going to present the image segmentation, image clustering, image labeling, image shapes, identifying image shapes. All these things mean the same. Image segmentation, clustering, image shape, image identification, and so on. Image classification all mean the same thing in this case. There are small differences, but technically they are all same. Now, last time we presented what is called UNet method. That is a network that resembles like a U-shaped network, okay? And we are going to review quickly, for 10-15 minutes, we are going to review that so that everybody is on board, we are all coming together again. And the next topic we want to tell you is that we have an alternative method because there is an issue about neural networks. These are all, you might be, you should not be confused, okay? We are here to explore, understand the landscape and make good choices in our applications. So these neural networks have some very important characteristics. One is that they are huge number of parameters are involved there. Huge. In fact, I know a network that involves 130 million parameters. Okay, huge number of parameters, and they take a long time to compute. But here is a method that we are going to alternative method, what is called the density base. How dense the points are going to determine the shape, are going to determine the segment, are going to determine the cluster name. Okay, and that is called what we are going to call is image segmentation approach using DBScan. Image segmentation approach. So we are going to talk about that. So then we go back and use this in the application of determining nuclei classification, so nuclei segmentation. Okay, I'm using a little bit loosely the classification and segmentation same, but it is nuclei. We are given an image of nuclei, and we are going to determine its how many nuclei are there. Okay, So that's our purpose. So three parts to it: reintroduce, we go back and refer the unit again, just to recall what we have done, and then we are going to do. And it's a good method. And then we are going to do, image segmentation based DBScan method, statistical learning method, and compare the results using the codes that we have. This is a research, kind of cutting edge research, but it is working. We find that it's fascinating and it's working, and you can apply. That's our claim. Okay. Now I want to invite my colleague Jessel to start the presentation. Go ahead, Jessel. Thank you very much. Thanks. Oh, by the way, before we start, do you have any questions? Any questions that I can answer? That's another thing. We are very happy if people ask questions. I think our purpose is really to create an awareness, create your ability to understand and interact with us. We consider that as a success measure. Okay, when you interact with us, we consider that as a success measure. So, any questions, please? So, please feel free to pose the questions. I will get attention from JK. Just any questions now? It's pretty quiet. Can I take that? No questions? At least somebody say no. Okay, but I know that it's working. Okay. Our connection is working. It's pretty quiet. All right, I'll pass on. Okay, thank you, Anurag. I appreciate your responses always, Anurag. Thank you very much. Take it over, Jessel. Thanks a lot. Jessel, we can't hear you. I can't hear. Say hello and then start. I'm not able to unmute. Oh, okay. 1 second. I may have to do unmute. 1 second. Sorry about that. I may have
I'll
to do that.
Yeah, sure. Okay, now it's fine, right?
Keep going.
Okay, cool. Sure. So let's just
raise the volume, please, on your side.
Volume of
volume raise. Yes, make it yes.
Okay. How's this now? So just to review what we did last.
Just please ask other people in the office to be quiet. It catches up. And also those who are joining, please mute out your phone. I appreciate that. Excellent. Thank you. Go.
Okay, so you can hear me now? Is it fine?
Yes, go.
Sure. So first, let's review what we did last time. We had done various structures of neural networks in the previous months. Last time we looked at a specific type of convolutional neural networks. Convolutional neural networks are specifically, network architectures designed for image analysis, and particularly we looked at what is called a unit. So just to review the problem that we had. So we had basically we were given images of cells, and the task before us was to identify those regions which the nuclei of the cells occupied. So given an image which is in the computer, it is stored as a set of pixels, rectangular shape. Some of the images are colored, some of them are black and white, some of them are having a bright field like this one or this one. Some of them are from a dark field. So there are various colors, various backgrounds, various lighting, and the ideal job was to, across all of these various types of images, to identify those regions where the nuclei were given. So we were given essentially a set of images and also given a set of masks, or what is essentially the target labels. That is what you are asked to predict. For example, you were given a set of images and then asked to predict, okay, which are the regions where the nuclei are located. So the word mask is used because the mask that covers your face covers the entire face, except of course the eyes and the nose and the mouth, which are the regions of interest. So we are asked to identify certain regions of interest in an image, and so we call that a mask. So the goal is to identify the pixels where the nuclei are located. So given this kind of problem, we looked at how this is different for compared to image classification. So image classification, you're given a set of images and asked to classify, is it a cat or a dog or a plane, or what is there in the image. Essentially, you're asked to put a label on the image as a whole. Whereas here, it's different. You're asked to essentially put a label on every pixel and say whether it is inside a nucleus or outside the nucleus. So it's different from labeling an image. You're asked to actually label every pixel of the image. And then, okay, so this is standard image classification technique where you're asked to label what is the handwritten digit that is given. So we have here images of handwritten digits, and you're asked to identify which of the 10 digits it is. Is it a 0 or a 1 or a 2? So essentially, it's a multi-class classification on an image. Whereas what we have here, or what the problem that we have tried to do was to use a what is called a unit, which is used for image segmentation. So that gives essentially an output for every pixel and allows you to predict whether or not every pixel in the image is belongs to the cluster or it belongs to a background. In this case, what I mean by cluster or background is whether it belongs inside the nucleus or whether it belongs outside. Okay, so this we did last time. We looked at what does unit do, how it uses convolution to identify the regions, and what kind of structure there is. In convolution, you have you go from layer to layer, essentially by doing some linear transformation. On top of that, a non-linear transformation, and so on. Then you go down this called max pool, and then this U-type architecture, which allows you to actually bring down the number of pixels and then bring it up again, so that the output so that you get one output for every pixel that was given in the input. And this I'm just rushing through because we had gone through this last time. We looked at what needs to be done here. Generally, you pre-process an image. The images, for example, in any kind of neural network problem, you have to send in images batch by batch. And what we were given here is the original set of images were of various sizes. The heights and widths were of various sizes. Some of them were 256 by 256. Some of them were 1024 by 1024. So all of that had to be normalized. If you want to, so they all have to be put together in the same shape and size if you want to use CNN. So anyway, we showed an example of how this is done in an R code. We looked at what was a unit application in an R code. We calculated certain value of accuracy of the prediction. So in this case, I think we had calculated the value was around 0.14 for a unit with some 100,000 or 200,000 parameters. Okay, so this was the neural network approach for solving the problem. Now we want to look at the thing now in a totally different approach, what is called the DBScan method. Okay, the same problem, but let's try to look at it from a different angle. So first of all, why? Why is it that you want to look at it in a different angle? First of all, see the neural network that we saw last time. It's a huge algorithm. You need to have hundreds of thousands. You can even have billions of parameters for the really advanced neural nets. It takes enormous amount of computational effort to train them. Then you have to do things like image augmentation. The images are not so if you are given only a few images, you need to do some transformations, make the images more in number by, say, doing some translations, rotations, and you do image augmentation. The parameters, because of the enormous number of parameters, there is a problem of overfitting. You might overfit, and then there are all sorts of other things you have to do, like dropout. So it seems that this seems to be a rather roundabout way of tackling the issue. Why can't we do it in a simpler way? As Dr. Netra was saying, finally in DBScan, what you're worried about is you want to take an image and identify which regions are dense, which regions are rare. Now we have to define dense and rare properly. But what DBScan does is simply identify which regions are dense, which regions are rare in a certain set of points. So we are looking at it in a different way, and we'll see that this actually requires far fewer number of parameters. It's computationally much cheaper. There is still, if you want to compare it with the state of the art in terms of neural networks, there is still a lot more to go to make it as good as the state of the art neural networks. But still, this is definitely worthwhile in terms of the sheer simplicity, also the simplicity of understanding. You are able to understand it intuitively. Unlike, say, the parameters of a neural network, so if you just stare at the matrix of kernels and biases and weights, you won't understand what is going on. The computer knows, but you don't know. Whereas here, you can intuitively understand what's going on at every stage. So let me first introduce DBScan. So suppose it's basically a clustering technique. Suppose you have a set of points, some of which are closer to each other, some of which are further apart. DBScan is a clustering technique, sort of like K-means clustering or some clustering technique. You are basically putting the set of points which are related or closer to each other into one cluster, and another set of points which are closer to each other into another cluster, and so on. So the way you do that is that you take a point and then you look for a neighborhood around that point, and you define that neighborhood as a certain distance. So there is a parameter called epsilon, which defines the region of neighborhood around a certain point. So every point you have a region of neighborhood, which is a set of all regions where, say, the distance from that point to anywhere inside that region is less than epsilon. So epsilon is a parameter. And then you classify a point as what is called a core point if there are a set of min points, number of points that are inside that region. So if you have a lot of points inside that region, then it's a core point. If you have only a few points, it is not a core point. We'll see how it works. So basically, suppose you take this point and look at a ball of radius epsilon around it and see how many points are there. 1, 2, 3, 4. So you include the point itself. So there are 4 points. So then you put a cutoff and say that, well, all points suppose which have, say, more than 4 points within the certain radius, they are called core points. And then you draw a line connecting them. So you start with this core point and then connect these 3. And then now you go to the neighbors and then start drawing again. You draw a region of size epsilon. So you look within the neighborhood of size epsilon and then find out which are the points which are neighbors and connect them. And if they're greater than a certain set number of points, so min points is also a parameter. Okay. So this is useful for putting together, and once you connect these points like this, they are all connected and they all become one cluster. There may be another cluster which is unconnected. There are points which are outside every cluster, which are basically isolated, and they don't have enough number of neighboring points. They are called noise points. So if you have data which consists of points which are closer to each other, we want to put the points that are closer to each other into a single cluster. DBScan is the way to go. And the advantage with DBScan is that it doesn't care about the size of the clusters. You can create clusters of any size that you want. You can create clusters of any shape that you want. For example, if you're given this kind of set of points, DBScan will immediately identify. So the clusters have now been color coded essentially. So after doing DBScan, you're able to put all of these into one. You're able to put all of these into one. Put all of these into one. Doesn't matter what the shape is. Unlike, for example, K-means clustering, where the shape has to be somewhat round. Whereas here, it doesn't matter what the shape is. You're able to put them in clusters. So how do we connect this now to our images? So this is the usual DBScan, where you have points which are closer to each other in the dense region are put together, and points which are further away, suppose they have no points nearby, they are just called noise points. Now, when it comes to image segmentation, well, okay, the whole procedure we will go through. First of all, you read the image data. There are certain steps of pre-processing that I had explained last time, but we'll go through this again. For example, if you had an original image like this, we basically identify the region where there is a kind of constant color as probably the background. So the background is where there's a constant color. So we identify that as the background. We set that to 0. That is to say, if the background was originally white, you set that to black. And then you normalize the image. Essentially, you divide by the mean and things like that, so that the image becomes more, you're able to process the image in a better way. So this is the step that we do, just normalizing the image. This would, there are certain steps in normalizing even for neural networks. But so that's the first step. And then what we do is this. So now once you do that, think about this. What is an image? What we have here is that in every pixel, you have a value of red, a value of green, and a value of blue, right? So you have an RGB at 000, RGB value at 001, 002, and so on. So this is very different from the kind of DBScan clustering that we had seen there previously. There you had points which are, some of which are closer to each other, some of which are further from each other. Whereas here, what you have is just a square lattice where there is a uniformity of distance. We are just talking about the ordinary distance. The distance between 0, 0 and 01 is just 1. The distance between, it doesn't matter whether it's between these two, whether it is between these two. Okay, the distance from here to here will be square root of 2. So it's different. What you can't use the concept of density in terms of which points are clustered together in the usual sense of distance. What we need to do.
1 second. I want to reiterate this very, very important point. What makes this innovation possible? As JK mentioned, Justin mentioned, we cannot just use the Euclidean distance, which is requiring the XY axis type points, and then you find the distance between them using the what is called the Pythagorean diagonal type calculations. Okay, so it's really a new type of distance measure has to be defined, and that has to have 2 properties. And he's going to talk about it. So fundamental to this analysis and approach and solution is that we need to define a new distance, which will bring together, understand that it can give you a better measure of those points which are closer of the same type. Those points of the same type of color, they bring together those colors, and then they separate out from the background colors, very distinctly. So those 2 properties, if it satisfies the distance, that will be a very helpful distance, and that's what he is talking about. Okay, very different idea, very new idea, innovative idea. So, but it's working. Thank you, Jake.
Okay, so suppose so in this image, what you have? Well, you have a pixel 0, 0, and inside that you have a value of what is the strength of red, what is the strength of green, what is the strength of blue. Now, after normalizing the image, the beauty is that the background will be 0, 0, 0. If it is 0, 0, 0, it is a background. That is red, value of red is 0, value of green is 0, value of blue is 0. That is, if it is pure black, it is a background. Okay. And however further away from that it is, the more likely it is that it is part of a nucleus. Value of R, G, and B are large, then it is more likely part of the nucleus. So after pre-processing, that's what you have. So you have an RGB value here, RGB value here, RGB value. I have just simply identified whichever the regions of the nucleus as green, and here is the boundary of that. Whereas these black points are the boundary, say. Okay, so they are the background. Okay, so you have nuclei of various types, various shapes and sizes, and inside there the values will be far away from 0, 0, 0, or far away from black. whereas for the background you'll be having essentially black. Now we need to define a distance measure that will actually put the distances within each cluster to be small and between two clusters as large. So one way of doing that you might think is, well, suppose this is R1, G1, P1, and this is R2, G2, P2. What about simply R1 minus R2 plus G1 minus G2 plus B1 minus B2? Or rather, what about, so R1, G1, B1 is, say, a three-dimensional vector here. R2, G2, B2 is a three-dimensional vector here. So how about you define a distance so that R1 minus R2, G1 minus G2, and B1 minus B2, say the distance between those two is simply the difference in the color between the two. Well, that also won't work because you can have, say, a dot here which is R1, G1, P1, and you can have another dot on the other side of the image which also has the same color. And so the distance between them in that sense, R1, this might be R1, G1, B1. This also might just be R1, G1, B1. So you can't use simply the difference between the colors in order to identify a distance measure. What we want is a distance measure that will put all of these together, closer together, and all of these closer together. But this and this should be further apart. That is nucleus and background should be further apart, and nucleus and another nucleus should also be further apart, and background should be further apart. So there were two ideas we tried. One is two measures of distance. One is the measure of distance where it is proportional to the range of color variation along a path that connects two pixels. So we need to measure have a distance measure between two pixels where any path that traverses the distance between those two pixels, if there is some dip in the color, essentially it goes through a dark region or background region, essentially that should be increasing the distance measure. So basically how much of variation in color there is as you move along a path that connects the two pixels. Another measure of distance is essentially how much of background you have to traverse. If you have to traverse a background in order to connect two pixels, or any path that connects two pixels, if it has to traverse a background, then that means that the distance is large. So these are two ideas, and we wanted to essentially combine the two ideas. So I took a linear combination of the two concepts. So we both of these ideas, put them in the form of mathematical equations, and then developed a concept of combining the two. So here I've uploaded them in GitHub. The equations I've uploaded there. Let's take a look. Okay. So, right, let's see. Yeah, the distance measure, well, okay, we won't go into the mathematics of how I define it. Maybe there are better ways to define it, but these are two measures. And then I've defined finally a custom distance, which is a linear combination of the two. And there are parameters. So there's a parameter alpha, there's a parameter beta. And already in the DBScan, there are those two parameters, epsilon and min point. So these are actually just 4 parameters. If you can get out these 4 parameters, that's all you need. Then you just plug in the distance matrix, and you should be able to do DBScan on this. And DBScan will automatically identify for you the clusters. Okay. So the procedure was first read the image data, then do normalization or pre-processing of image. Then I talked about the relevant distance measure. Then calculate the distance matrix among pixels. So there's a little bit of some advanced computational ideas there. Like we have to use recursive algorithm to search through the various paths. We have to use we cannot. So the distance matrix will essentially be huge. Think about this. Suppose you have a 256 by 256 pixels image. So the total number of pixels is 256 square, which will be 65,000, etc. So if you want a matrix that measures a distance between every pixel and every other pixel, it will be 65,000 by 65,000. A huge matrix, so it will have to actually be a sparse matrix. You can't use a normal matrix for that kind of size. And there will also be these parameters alpha and beta, which right now are not determined yet. We will have to determine them essentially. So right now we have used just a heuristic approach, as we just looked for those alphas and betas that work. For a particular image, we look for those alpha and betas which work in giving you the correct kind of, at least the best image segmentation, one which is closest to the training output, the training level. Of course, so we will need to replace that with certain modeled estimates of alpha and beta. But those are the only parameters, as opposed to, say, in neural network, where you have hundreds of thousands to millions of parameters. Here you just have those four numbers, alpha, beta. You have those two values, epsilon and min points, which are coming from the DBScan. Okay, so once you have a distance matrix, you can apply the DBScan algorithm, and that will immediately give you, it will quickly, the calculation of distance matrix is what is going to take time, but once you do that, the DBScan algorithm will quickly generate the clustering. Okay. So the procedure is as follows: you feed the original image, send in, you get the processed image. Then you can, okay, right now we are guessing the values of alpha and beta, epsilon and min point. From that, do the segmentation. So this, what we are seeing here on the bottom right hand side, is the predicted segmentation. This is the actual segmentation. This is what you should get. This is what we are getting for one such image. We have done this for, we are just looking at the training data and seeing what kind of accuracy we are getting. So, so first of all, the parameters that we have currently, we need to have a model to generate them. Currently, we are just searching for the best alpha and beta to get the output, but finally we need to have a model to generate them. Given these parameters, if you are somehow able to generate the parameters, then you can get an accuracy of 0.4 in what they call mean average precision. So this is a certain accuracy measure which the Kaggle computation is using. So just to give, comparing to the UNet, which with the around 100,000 parameters, that was giving a mean average precision of 0.14. And this is giving actually a much better mean average precision with far fewer number of parameters. So this is where we are currently at our research. We have a lot more things to do. We actually currently at this stage we are having Python code, but in the future we'll be writing R wrappers to them, making them more efficient. So, Dr. Netra, is there anything you'd like to add? Hello? Hello?
Hello?
Yeah. Hello?
Yeah, you're audible.
Yeah. Now, is there anything you would like to add? Is there anything you would like to?
No, this is clear. So we would work with the code basically to understand it in further better way. It would be great if you can give some insight like mathematical background.
Yeah. Okay. I didn't want to go too deep into the mathematics. I thought I'd be leaving people behind. So, the concept of distance. Let us go actually look at the equation that I've used there. So there are two concepts of distance I thought of. At each point you have a RGB value. You have a amount of red, amount of green, amount of blue. And the idea is that in the background it is black, and if you are deep inside the nucleus, it is somewhere closer to white. So the concept of clustering is that you take, say, a pixel ij and you take a pixel k, and you take a path between the two. If on traversing that path, you have to actually change the color by a significant amount. So, for example, you're here, say, this particular region, and then to go from here to this, so here we have a dense white region, and then you have some rare white region. So, in order to change, go from path certain point ij to point k, and you're traversing a path, you have to actually look at the change in the color, or the change in essentially what I have defined here is norm of RGB. Nothing but along the path you just take the root of r square plus d square plus d square, or just the, if I say, the norm of the colors. So what I mean is black is 0, white is 1. So having that kind of a concept to move around there, and you see the difference between the two. And if that is large, well, in that case, then you're jumping from one from a region of a certain color density to a region of another color density, then most likely they belong to different clusters, and they should be put in different clusters. So the distance between them should be large. So essentially, the range of color variation, that's what I have defined along a path, and there should be at least one path with small range in color variation if you want those 2 points to be part of the same cluster. So what I am doing here is taking the minimum across multiple paths. So there are multiple paths connecting ij to k. So I take the minimum of this. This is the IN absent limits infimum. Of course, with that measure of distance alone, the problem is that the background will also turn out to be a different cluster, because the background is so we just take this particular region of the background and this particular region of the background. Well, there is essentially any path connecting the two will just pass through the background itself, which I have normalized to 0, 0, 0. So here also there's not much variation between the 2 points. So I need to add some more measure which will essentially make sure that if you are in the background, however much, so the minimum, that is to say, whichever part of the path that is closest to the background will be taken, and there, if certain part of a path connecting 2 pixels goes through a background, then that will increase the distance between the 2 points. So that is also another measure of distance defined. So both of these, there is a certain, we need to take a mixture of the two. So I just then multiply measure A with alpha, measure B with beta. These two values, alpha and beta, are yet to be determined. They are not given to us by the model themselves. So that remains to be seen at what accuracy we can determine alpha and beta, and how much of importance needs to be given to that. Do we really need to specify alpha and beta to a high degree of accuracy, or is it okay if you just take some values and will it still give you a very good outcome? And that remains to be seen. So this is the custom distance measure. Okay.
Really cool. So thank you very much.
Okay. So
one second, JK. Was there a question? I heard somebody talking.
I just thank you for the explanation.
Excellent.
okay.
Thank you.
All right. So I think I'm done here. I think I'll leave it open for questions or anything further needs to be discussed.
JK, can't talk clearly, please, because I'm not able to hear well.
Oh, yeah. Can you hear me? Is there anything further I need to discuss?
I don't know why.
Hello?
Yes, okay.
Is
Fine.
that
Better.
yeah, can you hear me? So the initial results seem to be promising. Just compared it with the UNet, we have actually given a much smaller mean average precision, even though not no parameters. So this is where we are at. Is there anything
there be any possibility for you to share the mathematical document to go through to understand this
Yeah, okay.
by a GitHub or any way?
So
Yeah, we will share that. Your name, please. I'm trying to understand you. Kavira. Yeah.
Kavira Shekhar.
We will put it through GitHub because we have now a GitHub account, and in fact, the codes will be used today from GitHub. Which is already posted there. We'll have to post the presentation deck also. You're right. Okay, we'll do that.
Yeah.
Thank you.
Yeah, sure. Thank you very much. Yeah.
okay, so I think I'll leave it open for questions now. Okay, there was a question of what is the advantage when DBScan is used over UNet CNN. First of all, the advantage is computational simplicity. The number of parameters is small. The computational effort is much less. Actually, I cannot at this stage. I cannot give you hard measures on that because, of course, the UNet architecture and all has been developed with TensorFlow, which is written in Python, C++, which is written in multiprocessing and other things. It uses all that. So currently the code that we have right now is just in pure Python. So I can't compare the two, but actually even there you can see that DBScan is much faster. And the number of parameters is fewer. It's much easier to understand the parameters. It's you can't. Can you get an intuitive understanding for say what the weights and biases mean in a neural network? You can't. Whereas here you have an intuitive understanding. If you can actually some parameters you can just set immediately. Look at, for example, min points. For DBScan, you have epsilon and min points. So you can immediately set min points as in this case as basically the number of points that you would want in the smallest cluster. If you are sure that any cluster will have more than 10 points, you immediately set min points equal to 10. You can easily do that. The other parameters are not that easy to determine, but you can have an intuitive understanding. Essentially, if epsilon is small, that means you are being more conservative in making sure that only really dense points are closer to each other, are considered as part of the cluster, and more go into noise. Whereas epsilon is large, then noise is it's easier to put points in a cluster than in the noise. Now alpha and beta, well, okay, they are also there are a couple of parameters which give certain weights to which concept of distance we are going to be giving importance to. Right, alpha gives importance to measure. More of alpha means more of importance to measure A. More of beta means more of importance to measure B. But it's easier to understand than the parameters of a neural network.
Any other questions? JK, did you cover in detail the codes also in the GitHub, from the GitHub? And
so the codes, okay, the codes are currently uploaded in GitHub. Sure, okay. How do we... So the procedure I have followed is simply this. You just look at the training data, you load the training data, which consists of the images and the training labels, which are essentially the masks. So if I go to the training data, it consists of, say, images and masks, which are sitting like this. So every single nucleus is a separate mask. What I have done initially is to just take them and combine all the masks together, and then find out those parameters, alpha and beta, which are best used to use so that the DBScan will then match as closely as possible the the training, the targets, the predicted, the training labels. So what we do is load the data, do the normalization, what I defined as the normalization. You set the background to 0 and all that. And then you calculate the pre-computed distance matrix. So use a pre-computed distance matrix between the pixels. And in calculating that, of course, you use the numbers alpha and beta. Then you optimize for the correct values of alpha and beta in order to maximize the accuracy. Now, of course, this is something that we will not be able to do for the test images. So we are just here looking for alpha and beta, which are the best values for generating for getting the highest accuracy for the training data, and then apply that and generate the segmentation. A few more examples of segmentation results. So the combined mask is just the total or the combined set of masks which are the training labels, and here is the predicted interior. Let's look at them side by side. So predicted interior is what I get from DBScan, and this is what it should be. What I get and what it should be. So
So how will you compare the performance?
Right now, see, as it stands, we need to find some way to generate the parameters alpha and beta. Otherwise, we can't really.
I can't hear you.
So just a minute. So right now, we need to find out a way to generate the parameters alpha and beta. Right? Otherwise, we don't know how to compare. Whereas, if you have the two values.
No, that's fine. You did estimate. No, that is fine. That's fine.
We just use the correct values. We kind of tweak the values to get the maximum accuracy for the training data. So there you get around 0.4 in terms of mean average precision. Whereas for a unit with 100,000 parameters or so, you get a mean average precision of 0.14. Just to get a comparison.
Yeah, there is a huge, with unit, there is a huge benefit with unit. Okay. So, but however, in the competition, we still, have to accomplish something.
Yeah, so competition, some of the best values are around 0.55.
Yeah, 0.55. But what is pointing out to us is that this is accomplishing what unit could not accomplish. Unit gave MAP error rate is 0.14 with 100,000 parameters. We are talking about only maximum 4 parameters, and then we are getting an accuracy of 0.4, and that is 40% accuracy. So as you can see, this is way different an approach, a strategy, an approach that can solve image recognition, image segmentation problems also. Okay, so that is the claim we are making here, and it's fascinating for us. It's we are very impressed with the accuracy levels. There is a lot of work that can go into it, and we can benefit. Reap the benefits of such very simple methods like what we call it as image segmentation based DBScan. Any questions? Please, it's your time. We love questions. One thing that you might have seen is that we talked about deep learning with R, but we ended up doing Python also because it is at a research level. Once this is cleaned up, perfected, we will convert this into R. That is our ultimate goal, definitely. But for intermediate development work, we find the Python is very helpful, and that's what we have done it. But eventually, this will be converted into R. Go ahead, Mr. Vishnu. Any questions, please? You can also type. while you think about your questions or to type, I want to invite your attention to next week, the coming week. We are presenting the machine learning method called recommendation engine that I did last month, but I want to explain to you how do we judge goodness of a machine learning recommendation method, okay? Recommendation engine. How do we judge goodness of method? And that we are going to do it for the movie recommendation engine, okay? So we will continue next week on the machine learning method called recommendation engine, and the purpose of next week presentation will be on measuring goodness of fit, goodness of the model. Okay, that's coming next week. While you are thinking about your questions, please go ahead with your questions. I'm kind of floored that there is no question at all. It's not that we make such a perfect presentation, but then so please feel free to interact with us. That's what makes this relationship presentation fascinating one. Okay, it's pretty quiet there. We will make our deck as well as the codes available in the GitHub. Can you please post the GitHub link here, JK? The other thing is, we'll have to post the presentation deck. Right now, we have the codes there. We will also post the video of whatever we have been recording, in today's session. Okay, we'll post that video recording in our Institute of Analytics forum. Okay, so video recording is coming. Here is the GitHub place.
I think you need to send it to everyone because I can't send it to everyone.
No, I will do. Oh, I see. Okay, I see. Thank you. So here is the link. I'm posting it here, to everyone. And we will also post the video that is being recorded now. It may take an hour or so at the minimum, and we'll post it our Institute of Analytics forum. The Institute of Analytics forum is given here. By the way, I just want to give you a quick introduction to Institute of Analytics. Institute of Analytics' purpose is really address the million+ jobs that are available for machine learning and AI that's either available today or are coming up pretty soon. Okay, in the next 7 to 10 years in India alone, 1 million+ jobs, fascinating jobs. That's a new modern job opportunities. So we want to address that in training under Institute of Analytics. That's what we do. And we do that. Yeah, I'm sorry.
There was a question about
okay.
What are the other standard image? What are the other standard image segmentation techniques? Well, we have not tried others on our own, but we have just seen, generally the kind of results there are is for the state-of-the-art UNet and other type of CNN models. You have something like 0.4 to 0.5. I think there is a something called mask RCNN. It gets you about 0.5 in terms of MAP. So this is just the talk. I have not yet. We have not done the codes or run the codes ourselves. But I think the best is right now mask RCNN. So that is the state of the art.
Mask RCNN is what JK is saying. Mask RCNN. Okay. All right. Thank you. So there are no other questions right now, and we will call it a day for today. Next week, same time, we have recommendation engine, evaluating recommendation engines. Okay, I'll review quickly recommendation engine and then spend more time on evaluation of recommendation engine. Thank you very much, everyone. Have a great rest of the day. Bye-bye.